Welcome back, everybody. We're about to start a couple of videos here on the comparison tests. So this is part of our sort of ongoing theme that we have, right? We will have lots of examples of series. In fact, these examples are extremely important for what we're going to be talking about today. And then we'll have lots of tests. So far we have a handful of examples. We only have a couple of tests. We'll have many more by the end of this. And the idea is you're given on the exam a series that you have no idea whether it converges or diverges. And the question is, figure out which it is. And of course, show all the work necessary to prove that. In other words, do a test of some sort, tell me the name of the test that you used, show all the work to do the test, and then tell me, whether it converge or diverge. Just putting converge or just putting diverge, you got a 50-50 chance of getting it right, but you don't get any points for that. So let's get started with the first one. The first is the direct comparison test. This is what our textbook will call it and what most books call it. I will probably slip up several times and call this the baby comparison test. The reason is this is what my calculus teacher called it. So I really liked my calculus teacher. He was very funny. And he had just come to the U.S. from Germany. And when he would talk about various parts of calculus, he would often, make slightly derogatory and, and humorous, intentionally so, not being completely serious, comments about the relative merits of the U.S. and the German educational system. And so I'll never forget when we got to the direct comparison test, he said, yeah, guys, we call this the baby comparison test. Yeah, we do this in the German kindergarten. so I've never forgotten that part. So if you want to think of this as the German kindergarten test, whatever, I know he was kidding about that. But so how do we do this baby version of the comparison test? We'll have a stronger version later, which is hence the name. Well, if we have two sequences, right, and say that neither one of them are negative, so AK and BK, they're both bigger than or equal to 0, and let's say that the BK is the bigger one, right? Bigger than or equal to the AKs. So maybe if we graph these, they might look something like this, right? With the BKs on top of the AKs. This is kind of the picture to keep in your head of what these might look like. Okay? And it's always that way. All the way out the sequence, the red BKs are always bigger than the blue AKs. Now, if that's true, right, then think back for a second to what we talked about with the integral test, right? That the sort of the series and the integral, if we set things up correctly and the pictures look more or less like I've drawn them, they should do the same thing. In other words, if the series converges, then the area from the integral test should also be finite. Okay? And so this maybe will make this make a lot more sense. It'll be sort of obvious because if the series of the BKs converges, in other words, if the big series converges, right, then of course the smaller one, well, is smaller, right? So it can't go off to infinity. It's got to converge too, right? So imagine this, if I were standing in, of course, and I'm sitting here in front of my monitor doing hand motions, right, which of course you can't see, and I'm not about to record myself because it just really looks really silly. But what I would do is in classes, I would hold my hand up really high and say, here's the BK, right, the big one, and then it sort of pushes down on my hand, which is below it, on the AK series. So if the big series converges, then of course the smaller one, well, it's got to converge too. And it works the other way, right? If the small one diverges, if the small one adds up to infinity, then the bigger one obviously is even bigger, so it's going to diverge also. Right? And so keeping this picture that's in the bottom of your screen in mind really helps, right? If the small one is infinite, the small one is too big, the big one's even bigger. On the other hand, if the big one is small enough, right, the big one converges, the small one has to converge too. Okay? Now, one quick aside, right? This will be true for any of the comparison tests we're going to talk about, as well as the other tests we'll talk about in the next several videos. We need all these terms to be positive, or at least not be negative, right? Here's why. Here's an example. Right? So in this simple little example, 1 over k squared, right? Well, that's bigger than negative 1 over k. The reason is negative 1 over k is negative, right? 1 over k squared is positive. But if we think back to what we know about p series, right? The series Again, I haven't written the sum in front, so right now this is written like a sequence. But the series 1 over k squared would converge because this is a p series with p equal to 2. On the other hand, if I put a sum here, right, in front of the negative 1 over k, that's minus the harmonic series. And of course, the minus doesn't change whether it converges or not. So this is a p series with p equal 1. It has a name. It's the harmonic series. This guy diverges, or the sum would diverge if I put a sum in front of it. So you see what's going on if I draw this picture is the big series is up here. Right? The smaller series, though, is well, it's down here. And it could be as big as it wants to be, just negative. In other words, things might be adding up to minus infinity down here, even though the red series on top there converge. Right? So that's the reason why we have to throughout all these next several tests, have terms in our sum, the sequence that we're adding up. Because remember, a sequence is a list, and a series is the list added up. So what we need to have happen if our comparison test or the next several tests are going to work is we need to have all the terms in our sequence that we're adding up all be positive, or at least not negative for some of them. Okay, so that's the problem, right? In this example, the bigger one, right, 1 over k squared, the bigger sequence, 1 over k squared, right, converges. But negative 1 over k diverges, again, because it's negative, right? It goes to minus infinity when you start adding those terms up. Okay, so let's actually do an example where we can do the direct comparison test and see something that works, not just a warning of what could go wrong if we did it badly. So here's log of k over k. So we go, okay, what do we think happens to this? Well, if the log weren't there, that would be just the series 1 over k. And we recognize that one from our list of examples. In fact, this is often the way you want to do these problems, is look at it and go, that looks kind of like an example, right? And could I make it look, make it change something to make it be that example? So if we just got rid of the log, right, then we'd have the harmonic series. And by having the log in the denominator, in the numerator, having that log in the top makes the whole fraction bigger, right? So log of k over k is bigger than just 1 over k, because of course log will be bigger than 1 once you have a big enough k. So this is great. This is perfectly set up to use the direct comparison test, because the series 1 over k, right, this blue smaller one, right, that's the harmonic series. It diverges. The sum of 1 over k diverges. So that means the even bigger sum, log of k over k, has to diverge too. Okay? So by the way, this screen gives you a good idea of what you would want to actually write in your homework and on an exam. So what I have done is I have said whether it converges or diverges, and I've given the name of the test I'm using, and then I have done the work necessary to use the test. In other words, to do the direct comparison test, I'd have to, compare it, right? Take my original series, or the sequence that I'm adding up to make a series, and say that that's bigger or smaller, whichever way I need to do, than some other sequence, and then say that when I add that sequence up, then it diverges or converges, whichever way it goes. So this part is the work necessary to do the direct comparison test. Here's where I say that I've diverged. And at the very bottom, I say I diverge by the direct comparison test. And I've named the test I'm using. Okay, here's another one. Does this look familiar, right? Does this look like another series? Well, if that 5 in the denominator weren't there, then that would look like a geometric series, right? It'd be 3 over 4 to the k. That'd be a geometric series. And so what would happen if I got rid of that 5? Right? If I got rid of the 5, then I would make the denominator smaller, because I wouldn't be adding the 5 to it, right? So if I just put my finger over the 5, then I have made the denominator smaller. But making the denominator smaller makes the whole thing bigger. This makes sense to everybody? So thinking through that little chain of logic is something we'll have to do a lot here. Right? So if I put my my thumb over the 5, right, then what I have done is made the whole denominator smaller, which makes the entire fraction bigger. So I have just 3 over 4 to the k, which will be bigger. Now, of course, 3 over 4 to the k I could rewrite as 3 times 1/4 to the k, so that it's obviously a geometric series. It'll be a geometric series with the a equal 3. The common ratio, the r, is a fourth. And that's great because having a fourth, right, as my common ratio means that my geometric series converges. So again, that's the work I need to do to use the direct comparison test. So because the bigger series converged, it means the smaller one converges by the direct comparison test. Okay, here's another example. So 1 over 4 square root of k minus 3. Okay, what does that look like? Well, if the 3 weren't there, it'd be a p-series, right, with a 4 in the denominator. And again, multiplying by a constant doesn't matter. Just like with an integral, you can always factor the constants out. So if I got rid of that 3, I'd have a p-series where the p equals a half. Well, what happens if I get rid of the 3? Well, I'm subtracting 3 now, so if I stop doing that, then I'll make the denominator bigger, right? Which means I made the whole thing smaller. Okay? So by not subtracting the 3, I have made the denominator bigger, which makes the entire fraction smaller. Okay. All right, so this is perfect because the smaller sequence, 1 over 4 square root of k, right? Well, if I add that up, that series would be a p-series with p equal a half. That diverges. So now my smaller series diverges, which means my bigger series diverges by the direct comparison test. Make sense? So again, why do we call this a comparison test? Well, we're comparing it, right? And this is why those examples were so important. You've got to have a whole store of things that you need to that you can fall back on when you need to compare things, right? Again, the most common thing for the direct comparison test is to look at it and go, oh, you know what, that's a p-series. Well, almost. If I erase that minus 3, all right, or that plus 5 or whatever, then it would be what I want and we'd be set. But this baby comparison test, right, the direct comparison test, it doesn't really help with one like this one, right? Let's see what goes wrong. If I were to erase that plus 3 in the denominator, well, plus 3 in the denominator is making the whole thing bigger. So if I erase that plus 3, I'll make the denominator smaller, which means I'll make the entire fraction bigger. So far, so good? In other words, if I erase that plus 3, I will have made the denominator smaller, which makes the entire fraction bigger. Oh dear, okay, why is that a problem? Well, now the bigger one is my p-series with p equals a half. And remember, if p is equal to a half, that series diverges. Okay? Again, not only do we have to know a bunch of examples so we recognize stuff, but we have to know what the examples do, right? That when you have a p-series with p equal a half, then that's going to diverge. So the big one diverges. Oh dear, right? We haven't said this before, right? But it's obvious when you think about it. If the big series diverges, the small series, well, I don't know, right? It might converge, it might diverge, right? Just because, you know, a big number is really big, it doesn't mean that everything smaller than it, is really big or really small. It could do either one. So just knowing that the big red series diverges, the small blue one might diverge, might converge. Just comparing them like this doesn't really help. Okay. Again, this is an easy mistake to make, to think that that I can always get an answer from the direct comparison test. The direct comparison test and the more powerful version, which will follow, both of them. Well, there's a possibility that we try the test and it just doesn't work, right? In other words, it doesn't really help because we do the obvious comparison, right? We get rid of that plus 3. We're comparing it now to a p-series with p equal a half. That's great, except that the bigger one, B series with a half is going to diverge. And if the big one diverges, it doesn't tell us anything about the small one. And of course, if the small one converges, it doesn't tell us anything about the big one. So there's an obvious loophole here, right? Where you could try the comparison test and it just doesn't tell you anything because you're comparing it to something that doesn't really help. So what we need is a more powerful test. And we'll get that in the next video.